Hi guys, in this session we are going to understand a very interesting instruction called as XLAT. What XLAT stands for? It stands for translate. You might get wondered what 8086 is really translating. Let us try to take one example. Suppose we have a MUPI 8086 here, and let's say it is interfaced with a device called as LCD. LCD stands for liquid crystal display. So on LCD we can display anything, like we can display right from A to Z, that is alphabets you can display numbers, you can display some symbols and so on. Let's take an example of number. Let's say if I want to display 3. So by general practice you load this 3 into any register, let's say AL, and then you send it to LCD. What we really expect that this 3 should get displayed on LCD. But let me tell you, this is not the way it works. The reason is LCD doesn't understand 3. Let me tell you, 3 is understood by you or maybe at the most by 8086, but LCD understands only ASCII values. Hence, it is very important, if you want to display 3, you shouldn't actually send 3. You should send its ASCII value. Let me tell you, the ASCII value of 3 is 33. So what you do is, first of all, you convert this normal 3 number into its ASCII value, and then only you send it via data bus to LCD. But LCD doesn't display 33. What LCD understands that 33 is an equivalent of 3, so it actually displays 3. Right? So let me take another example. Suppose if you want to display 5, you need to translate 5 into its ASCII value. Now I hope you are going to connect to this translate instruction. What I just said is, if I want to display 5, first of all I'm going to load that 5 into AL register. I'm going to somehow translate this 5 into its ASCII value, and in effect I do not send 5, but what I send is 35 via this data bus. But what gets displayed on LCD is not 35, it is 5, right? So I need some mechanism by which I can convert these numbers, or I can translate these numbers into their ASCII equivalent, and this XLAT instruction will help me to do this. By now you might have understood that 0 equivalent ASCII value is 30. For 1 we have ASCII value as 31. For 2 we have 32. I'm sure you can guess up to 9 if I go, the ASCII value for 9 is 39. So how do we achieve this with the help of this XLAT instruction is, we basically make a table called as a reference table. That reference table is also called as a lookup table. So what I'm going to do is, I'm going to make a table. Of course, that table is a part of memory. And let us try to store this ASCII value in this table. So let's say I have stored 30 here, 31, 32, 33, 34, 35, 36, 37, 38, and lastly we have 39, which is nothing but the ASCII value of 9. Obviously, when I make a table or when I'm storing these numbers into memory, every memory has some memory location number, right? So let us say this is stored in 2000 hex location. So 31 is present in 2001, 32, 2002, 2003, 2004, 2005, 2006, 2007, 2008, and lastly we have 2009. So what I'm going to do is, Suppose I want to display 7. Then my step number 1 is I should load that 7 into AL register. Then by referring this 7, you need to understand that you cannot actually send 7 to LCD. What you need to send it ASCII value. So guess where this 7 is stored. If you observe in this table, it is stored at 2007, right? So what you do is you basically refer this table, and therefore it is also called as a reference table, or it is also called as a lookup table. So you refer this lookup table and then you transfer this 37 to LCD. So for that, what you do is you do this by following this mechanism. So I'll tell you what is the mechanism. You need to understand what is the starting address of this table. As you can see, the starting address of this table is what? 2000. So 2000 is nothing but its starting address. Now, what is that number that you want to display on the screen? Answer is 7. So what I'll ask you to add this 7 with this 2000. What do you get? You get 2007. Look at this. This 2007 is nothing but the address where the ASCII equivalent of 7 is stored, and now you can send it to what? LCD. I hope you understand that. Let me take another example. For example, let's say if you want to display 8. So step number 1 is store 8 in AL register. Step number 2, add that 8 in starting address of this table. What is the starting address of this table? Come on, it is 2000. So add this AL with this. What address do you get? Come on, you get 2008. Now refer 2008. As you can see, 2008 has a ASCII value of 8. So what you are supposed to send to LCD is not this 8, but the content of 2008. So this mechanism only we are going to actually use in this XLAT instruction. So somehow you got an idea. So let's see. So the very first point is XLAT instruction works only on AL register. Please never ever forget that. Secondly, this instruction pulls the data from the lookup table. As we have seen, this instruction is going to pull up the data from the lookup table. BX register is the register which gives the starting address, right? Along with that, I'll add the extra point. AL register gives displacement. Right now you may not understand it completely unless we take some example. So let's say we have that table here. So 2000, 2001, likewise we have it up to 2009. So what is stored in 2000? ASCII value of 0. ASCII value of 0 is what? It is 30. ASCII value of 1 is what? 31. Likewise, the ASCII value of 9 is 39. So this is the lookup table that we have, right? So what you do is, you first of all take this starting address. Starting address of the lookup table is 2000. You load this starting address in BX register. Please do not take any other register. When I'm saying BX register, you have to load the starting address of this lookup table into BX register by writing an instruction called as MOV BX, 2000. So obviously after this instruction, what happens? It moves immediately 2000 hex into BX register. So what do we have in BX register is 2000. After that, what I do is, let's say whatever value that you want to display on LCD, you should load that number into AL register. Let us say if I want to display 1, then what I supposed to do is I should write MOV AL, 01X. Let me tell you, if you want to display 7, then you should write instruction MOV AL, 07X. If you want to display 9, then you should write instruction MOV AL, 09X, right? After this, the magical instruction, that is XLAT instruction. Now let me tell you what this XLAT instruction does. It loads AL from ds colon bx plus al. Now what does that mean? Let us see. See what bx has. Come on, bx has a value 2000, so it has value called as 2000. This 2000 will get added with what? Come on, it is adding with al. It is getting added with al, and what al has? 0 1. So what is 2000 plus 1? Of course it is 2001. So can I say that 2001 is the offset address? So from this offset address, that is from this offset address, it gets loaded into which register? AL register. So what comes to AL register is the content of 2001, which is 31. Can't you see that previously AL had data that is 01. Now it got translated into its ASCII value 31. So this is how this instruction really works. Okay, so let me give you another example. Let us say if the question is display 9 on LCD screen with the help of what? Translate instruction. So what you do? The only change you are going to make, again MOV BX comma, it should always have the lookup table ka starting address. Starting address is 2000. Then you are going to load this 9 into AL register. So you are going to write MOV AL comma 09 hex, and after that our magic instruction XLAT. So what is going to happen? Again it is going to add 2000 with 9, that is 2009, and content of 2009 it is going to load it into AL. Please do not forget what we had in AL is 09 before XLAT instruction, but after XLAT instruction what we will have in AL register, it is nothing but the content of 2009, so that is 39. So this is how this 09 got translated into what? 39. I hope you understood how this XLAT instruction works, right? Let me take one question very quickly. Write a program, WAP means write a program to get square of the number using XLAT instruction. So what we do is we are going to make a table very quickly. Let me give some address. Let me give some random address. Let's say 3000, 3001, 3002, 3003, 3004, 3005, 3006, 3007. Let me take two more locations here, 3008 and 3009. Now let me be very specific. Write a program to get the square of the numbers right from 0 to 9. So this program is valid only for having the square of the numbers ranging from 0 to 9 by using XLAT instruction. So what you do is step number 1, you should basically make a lookup table. Lookup table. So in this lookup table what you do is you store the square of all numbers from 0 to 9. So what is the square of 0? Of course it is 0. What is the square of 1? It is 1. What is the square of 2? It is 4. Like that. What is square of 3? It is 9. Square of 4, 16. Square of 5, 25. Square of 6 is 36. Square of 7 is 49. Square of 8 is 64. And lastly, we have square of 9, that is 81. Okay. Now, let's write the program. I'm sure you remember the steps. First of all, you have to initialize MOV BX, that is BX register, and BX register should always have the starting address of the lookup table, and in this case it is what? 3000, right? Then move AL comma. Now you can take any number from 0 to 9 whose square you want to calculate. Let's say 06, and then you just write XLAT instruction, and at the end AL should have what? 36. Let's see what happens in this instruction. So What AL actually has is DS colon BX plus AL's content. Check it out. What BX has? Come on, BX has 3000. What AL has? 06. What is 3000 plus 6? 3006. So from DS colon 3006, it means from 3006 location, the content is copied into which register? Of course, AL register, because AL is the destination, right? So what AL has is 36. So previously, before executing this XLAT instruction, we had 6 in AL register, but after execution of XLAT instruction, what AL has is 36. So this is how now we have translated the given number into its square. So let me tell you, the applications can be numerous. Like you want to translate the number into its ASCII value, or maybe you want to translate the number into its square value. Maybe you can take a cube of the number, or you can basically when you interface something called as 7-segment display. I'm sure you have seen something called as a 7-segment display, which looks like this. So this is what we called as a 7-segment display. And let's say if it is interfaced with MUPI, and if you want to send few numbers to display, again you cannot send 0 or 1 or 2 simply. You need to basically convert this 0, or you need to translate this 0 into its equivalent 7-segment display code, and then only you can send it to the 7-segment display. In that case, you can make a lookup table which will have the 7-segment equivalent displays of 0 to 9, and likewise you can again use translate instruction to send those numbers. I'm sure you understood this translate instruction. Okay, so in case if you like this session, please hit the like button, and be free to comment on this. Thank you.